What up, calculus students? We'll get into lesson 4, which is essentially just other types of derivative problems. We start with the slope equations of uh, the other trig functions. We transition into some higher order derivatives, like second derivatives, third derivatives, 52nd derivatives, slopes of slopes of slopes. We talk about what it means to be differentiable, and then we get tested on differentiability through piecewise functions. And then we got these table problems, which are called notational derivatives. So it's kind of a big lesson in terms of the different types of questions asked of you. It's bigger than the last lesson, which is really just a repeat of the second lesson with the product and quotient rule. So let's get into it. What I like to say is make sure you know sine, tangent, and secant derivatives, slope equations. And if you know sine, tangent, and secant slope equations, you can figure out cosines, cotangents, and cosecants. What do I mean? Like sines, slopes are cosine. It says figure out. Gosh, I'm just really messy right now. Cosine slopes are negative sine. Tangent slopes are secant squared. Cotangent slopes are negative cosecant squared. Secant slopes are secant x tangent x. Cosecant slopes are negative cosecant x cotangent x. So we kind of see how things are related to each other and try to minimize all that you have to remember and figure out some other stuff. All right, I'm just going to get to it then. Okay, I got 4 secant. What's the slopes of 4 secant? The slopes of 4 secant is 4. It's just a constant. Leave it. Times secant x tangent x. That's the slope equation of secant at pi over 3. I have the secant of pi over 3. There, write down. The tangent of pi over 3. Look at that. Trigonometry. Never disappears. Always need to be ready to do it. Cosine of pi over 3 is a half. So secant is 2. So I got a 4 times a 2. Tangent of pi over 3 is root 3 over 2 divided by a half, which is root 3. And you need to be able to figure that out. If you can't do it in your head, like I did it, draw your triangles. Pi over 3, root 3 over 2 is the opposite. A half is the adjacent. The hypotenuse is 1. Tangent over 8. Oh, we're dividing by 8. That must mean we have to use the quotient rule. No. No. Write it as 1/8 tangent x. Write it as 1/8 tangent x. Don't use the quotient rule, but if you did, you would still get the right answer. 1/8 secant squared x is the slopes of tangent x over 8. If I were to plug in pi over 3, I would need the secant squared of pi over 3. I need the cosine of pi over 3 flipped squared. So I got 1/8. I got the cosine of pi over 3 is a half. I then square that and flip it and square it. See, maybe it's like easier to write it as I need the cosine of pi over 3. I need to flip that and square it. Cosine of pi over 3 is a half. Flipped is 2. 2 squared is 4. So I have 1/8 times 4. I get 1/2. I threw this in. A lot of people were like, I guess like secants. It's like, no, no, no. That'd actually be going backwards, which we'll do in the future. Rather, just like be careful. They sometimes will try to trick you by showing you something, and then you have to realize, oh, this is a product. Secant x times tangent x. I have to use the product rule. This is a first, this is a second. Slopes of the first times the second plus the slopes of the second times the first at pi over 4. So the cosine of pi over 4 is root 2 over 2. If I flip that, I get 2 over root 2, which is actually just root 2. Multiply the top and bottom by root 2 over root 2. You get 2 root 2 over 2, which is capital be root 2. So all that to say that you need to figure out that the secant of pi over 4 is root 2. The tangent of pi over 4 is 1. Secant squared, that'd be root 2 squared, which is 2 times root 2. So this is a great question. I got root 2 plus 2 root 2's. I have 3 root 2's. So getting the slope equation, then knowing what to do with it. I'm not worried about this divided by 4. I'm going to write it as 1/4 cotangent x. I'm doing this just so like you see it often and you're not intimidated by it. Leave the 1/4. The slopes of cotangent are negative cosecant squared. Don't think of it's 1/4 minus cosecant squared. Think of it as 1/4 or negative 1/4 times cosecant squared. Like the negative can be moved over. What students sometimes do is if they put the minus sign in the middle of a product, they think it'll be subtraction. So don't make that mistake of thinking it turns into subtraction. I need that at pi over 3. Okay, so cosecant's the reciprocal of sine. The sine of pi over 3 is root 3 over 2. I'm going to flip that and I get 2 over root 3. I need to take 2 over root 3 and square it. Again, just to show you the steps, we would want to do cosecant squared, which is 1 over sine squared. So I get 1 over root 3 over 2 that I need to square. I need to get 2 over root 3 and square it. I get 4/3, which simplifies to be negative 1/3. Sorry if you don't have that much space, but these are good problems. They're simple. There's a lot of practice of trigonometry. Good ones. 3 is not bothering anybody. Leave it. Slopes of cosecant are negative. Cosecant, cotangent. I need to find those at pi over 3. Why did I stick with pi over 3? Why don't I go in a different quadrant? I wish I went to different quadrants. Okay, sine of pi over 3 is root 3 over 2. Flip it. It's 2 over root 3. Cotangent of pi over 3 is adjacent over opposite, which is a half divided by root 3 over 2. A half divided by root 3 over 2 is 1 over root 3. This is great. I get negative 6 over 3, which is negative 2. Fantastic. What about this one? Okay, the x over 3. I guess I don't have to worry about it. It's like, well, pause. X's times X's. I have to use the product rule here. I'm going to probably start by rewriting it as 1/3 x times cosecant x, and then slopes of the first times the second, plus the slopes of the second times the first at pi over 6. Cosecant's a reciprocal of sine. The sine of pi over 6 is a half. So I'm going to flip that and it's 2. Start with your triangle if you want to, your pi over 6 triangle. Okay. Now I got a -2. Cotangent is adjacent over opposite. Cotangent √3/2 over a half, which will be √3. Oh, and now I have a pi/6 in there. Probably not going to want to simplify this much. I got 2/3 plus -2 √3 pi over 18, which turns into over 9. I could change this to 6 over 9 if I wanted to. Probably not going to see this on a test. -6 minus √3 pi over 9 as your final answer. Just make sure you have the derivative down, and that's correct. You're good. The next two are just like preparations for derivative rules, notational derivatives. I want to find the slope of h at x equals 1. The slope of h will be, okay, the slopes of g plus the slopes of f. The slopes of h at 1 will be the slopes of g at 1. The slopes of g at 1 at 4. Slopes of f at 1 are 5. So I get the answer 9. But heads up, just make sure when we switch to notational derivatives, we don't forget our rules. Even if it's not x's and sines and cosines and tangents and cotangents, rules still matter. So here, if h was g times f, my slopes of h would be g slopes times f, that's the slopes of the first times the second, plus the slopes of the second times the first. And then if I want h prime of 1, I need g prime of 1, the slope of g at 1, which is 4, and then f of 1, which is 3, the slope of f at 1, which is 5, g of 1, which is 2. I get 12 plus 10, which is 22. Okay, now I'm putting these in your homeworks. I'm going to give you one on your quiz. This is just keeping the origin of the slope equation in our brains. We have to remember that Newton said, hey, take a slope, put it with a limit, and you will talk about a derivative. You'll get a tangent slope. He used this slope equation, which is two y's, 2 points, h distance from each other. Now you're thinking it's an x2 minus an x1, and it is, but they're saying like the x2 minus x1 is this x distance, we'll call it h. And these 2 points are this h distance away from each other. They said if we put the 2 points really, really close together, boom, this is a tangent slope. This is the definition of a derivative. You see this question. You're like, oh, it's a limit question. Oh, I guess I gotta no. It's like I gotta try to plug in 0. No, I gotta try to plug in -0.001, 0.001. No. Instead, you're like, yo, they're just asking me for the slopes of secant. This is a limit. This is a slope formula. This is the definition of a derivative. They're looking for the slopes of secant. Your answer is secant x times tangent x. How do you do that? It's not through a process of doing the limit. It's through a translation. It's like this limit and this slope is combined. This is a tangent slope. I'm translating this from a limit question to really being like, oh, what is the slope equation? What is the derivative of secant? This is a little bit more advanced. This is the slope of tangent at x equals pi over 4. Like, how do I know that? Because I see, like, as x approaches pi over 4, I'm going to be like 2 points really close to pi over 4. I'm going to be talking about, like, the slope of these 2 points infinitely close together on the tangent function at x equals pi over 4. I translate this limit question to be a slope question. Now, this is going to be on your quiz next class. So, I should have put it on your notes, but I didn't. The slopes of tangent, if y equals tangent, the slopes of tangent are secant squared. If you want to write it as secant x squared, just because you know you're going to use it, that's fine. Cosine of pi over 4 is root 2 over 2. Secant of pi over 4 is just root 2. Squared is just 2. Cool. What is the second derivative? It's just the slopes of the slopes. It's a f double prime. You find the slopes of y, you then find the slopes of y prime. Secant is secant tangent, cosecant is negative cosecant cotangent. That's the first derivative, the slopes of y. Now, what are the slopes of this? Now, I purposely give you this problem because, like, when we take the first derivative, when we find the slopes of cosecant, we end up with a product. If I want to find the slopes of that, I have to use the product rule. I have to have the slopes of cosecant, which I just found, so I'm going to do it again, only it's going to be positive. So here's the slopes of the first times the second plus the slopes of the second. I know tangent is secant squared, cotangent negative cosecant squared. Slopes of the second times the first. And you can simplify that if you want to. Y, we call this double prime. This is y's slopes of their slopes. It is cosecant x cotangent squared x. It is negative cosecant squared x. Here, nothing as crazy. I'd probably start by rewriting that as 1/3 x cubed. And the slopes are x squared minus 8x plus 0. The slopes of 2 are 0. And that means the slopes of my slopes would be 2x minus 8. The 52nd derivative of cosine, we did one just like this in class. We realized that things just kind of bounce back and forth with sine and cosine. Slopes of cosine are negative sine. Slopes of negative sine are negative cosine. The slopes of negative cosine are positive sine. The slopes of sine are cosine. We realize every fourth derivative, we are back to where we start, and then things repeat. Well, that means the 40th derivative is going to be cosine, the 44th, the 48th, the 52nd. 52 is actually divisible by 4, so the 52nd derivative is actually back to where we start. If I give you the first derivative, you have to recognize this is the first derivative, this is the slope equation, and I ask you for the third. You only have to find the slopes 2 more times. This is the third derivative, but you're not given y. So it's not like find the slopes of the slopes of the slopes. You're already given the slopes. You just have to do it 2 more times. Maybe it's important to keep track of notation. If you find the slopes of dy dx, that gets you d squared y over dx squared. Like the d's multiply together, the dx's multiply together. So anyways, we start with the slopes. Now we get our second derivative. We start with the first derivative, we get our second derivative. I have to use the product rule though. Heads up, x's times x is the slopes of the first times the second, plus the slopes of the second times the first. And then if I go one step further to get the third derivative, I have the slopes of sine, and then I have the slopes of cosine x times x, slopes of the first times the second, plus the slopes of the second times the first. I have 1x plus another, 1 cos x plus another cos x. If I want to simplify this, I would get 2 cos x's minus x sine x. I'm already giving you the first derivative the slopes of y. You're trying to find the fourth derivative. You just need 3 more derivatives. Keep track of notation, maybe. Slopes of dy dx, d squared y over dx squared. Of x squared minus 6. What happened to the 2? The 2 went away. (24x). It's just notation for the third derivative. And then, like, if I asked you for the 8th derivative, we should know that, like, it's going to be 0. If you start with a whole number, an integer, what do they call it? Natural numbers. If you start with a natural number, your derivatives will eventually work down to 0. Won't be the case for any negative exponents or fractional exponents. If I work through this, I realize, yes, this one goes away, but this one continues to grow. Cool. Now, next set of questions test us on understanding what it means to be differentiable. Differentiable means having a tangent slope. To have a tangent slope, you must be continuous, and you can't have any sharp points. A sharp point actually does not have a slope. A vertical tangent does not have a slope. And if you don't have a point, you don't have a slope. So these are the things that we check. Now, how we test you on understanding this concept of being differentiable is through piecewise functions, because there's lots of options for piecewise functions. One option is the pieces don't meet up. If the pieces don't meet up, obviously we don't have a slope here. Right there, okay? The other option, another option, is the pieces do meet up, but when they do meet up, they create a sharp point. This is a point where we still would not have a slope. What we want to check is that our pieces meet up, and they meet up in such a way that they meet up smoothly, that there is not a sharp point. This is how we're being quizzed and tested on being differentiable. We will check to see if our pieces meet up, and they meet up smoothly. Now, how do you check to make sure pieces meet up? Well, it's what we've done in the past. We check the one-sided limits of the function at the specific location where we're not using one piece, but we're using another piece. It's like the location where the left-hand limit and the right-hand limit use the 2 different functions. So I'm going to look to the left and I'm going to look to the right at 2 of f. And I'm plugging in 2 and I get 4. I'm plugging in 2 and I get 4. I said, hooray. But now we know this is true. But we could have a sharp point, or we could meet up nicely. So this is where the second piece comes in. We've checked the pieces meet up. We are potentially differentiable, but now, do they meet up in such a way so that there's no sharp point? Now, what we're going to do is we're going to check the slopes to the left and make sure they equal the slopes to the right. We have to do this extra step. This was, are you continuous? This is going to be the no sharp point part. We will make sure that the slopes to the left equal the slopes to the right. This is where we're going to need the slope equations. Now you can go back into the original and like create a slope equation that's piecewise. Okay, well, the slopes are going to be 2x for x is less than 2. The slopes are going to be 4 for x is bigger than or equal to 2. Actually, I'm going to start teaching it this way. Freaking love it. Like create the slope equation for f. This is great. So we had to create this. And now it becomes like a continuity problem. To the left of 2, okay, I'm plugging in 2 into here, I get 4. To the right of 2, well, I just get 4. Boom! The two pieces meet up, and they meet up in such a way that they meet up smoothly. We win. Are these differentiable? Yes. Is this piecewise function differentiable? Yes, everywhere. All right, cool. So like now we have now we have the ticket. We have the y. Why don't we have the f prime? This is great. I've never taught it this way. I've always just like said figure it out, but like this is perfect. If this is the y's, this is the m's. Check to make sure the y's are the same. Check to make sure that we're going to be continuous. Check to make sure the slopes are the same. Check to make sure we connect smoothly. You could just memorize the process. Oh, we got to do this and this. And it's like, yeah, sure, but just make sure you understand what's going on. Yo, 8 equals 20. No. These pieces don't meet up. No, that's bad. We are not differentiable. You might check here and you might be like, oh, 12 equals 12. Oh, yeah, the slopes are the same. So we are. No, the pieces don't meet up. So we have a situation where we're leaving one, we're picking up another. If they were to connect, they would connect smoothly. But since it's not continuous, we don't have a tangent slope. Good question. All right. We're talking about differentiability. We're talking about slopes. We might as well have a slope equation. We'd have 2x for x less than 1. We'd have 2 for x is bigger than or equal to 1. We'll check to the left of 1 the y values. We'll check to the right of 1 the y values. So I get 2 is equal to 4. Nope. I don't even have to check this. I don't have to check this. Don't have to check this. We are not continuous. So that means we are not differentiable. All right, let's come up with a slope equation. We would use 2x plus 0 for x is less than 3. We'd use 2 for x is bigger than or equal to 3. I will check the continuity part. I get 10 equals 10. Check. I will check the slopes part. Do they connect smoothly? Well, I get 6 equals 2. No. When they connect, we will go from steeper slope to shallower slope. We will create a sharp point when these two pieces connect. So this we could say we are not differentiable because we're not continuous. Here, we're not differentiable because the slopes don't approach the same value. Not because we're continuous, but we're not differentiable. Maybe we'll write that. We are continuous, but not differentiable. Here we're not continuous, here we're not continuous. Once you say you're not continuous, you know you're not differentiable. You can't say you're continuous and differentiable. So you would not say I'm continuous and differentiable. No. If you're not continuous, you automatically are not differentiable. Okay. Now we got this A and the B problem where we want to not only ensure continuity, but ensure continuity smoothly. So this is when like we're going to have this A and B, which are numbers. A and B are numbers. Just keep that in mind. We have the equation. Let's find the slope equations. Okay, well, I'd just get A for x is less than 2. Then I'd get 6x plus 0 for x is bigger than or equal to 2. Gosh, this is so great. Okay, Let's check to make sure we're continuous. To the left of 2, f values, the y values, do they equal the same as to the right of 2, the y values? To the left of 2, I'd get this here, 2a plus 5. To the right of 2, I'd get 12 plus b. Now, make sure there's no sharp points. To the left of 2's for the slopes is equivalent to the right of 2's slopes. Sometimes my cursor like freezes. Okay, limit x approaches 2 of the slopes equals the limit x approaches 2 to the right of the slopes. I get a equals 12. I plugged in 2 into this guy, or like 2.001, it's approximately 2. I get a is 12. Once you get a is 12, I get 29 equals 12 plus b. B has to equal 17. Cool. All right, same deal. Here is the function. Here are its slopes. I would have 2ax plus b as the slopes for x is less than 1, and I'd have 0 for the slopes that's bigger than 1. Slopes of 3, y equals 3 or 0. I'm going to skip the whole limit notation. I'm just going to get to it. Check the continuity. 2a plus b equals 3. Whoops, I keep messing up. Continuity here. A plus b equals 3. Check the smooth connection. Smooth connection. Over here. 2a plus b equals 0. You're plugging in 1 into the top and the bottom, just like I plugged in 2 here. I'm going to solve for b. Substitute in. Feel like I need to show the notation. Okay, what's the slope equation of this piecewise function? 2ax minus 0 for x is less than negative 1. 0 minus 2 for x is bigger than or equal to negative 1. Slopes of b are 0. The slopes of 3 are 0. Are we continuous? Plugging in negative 1 into the original function to the left and to the right, we get a minus 3 equals b plus 2. Do we connect smoothly? Negative 2a equals negative 2. Like the slopes are always negative 2 on the bottom piece. Slopes will change depending on what x is. Gotta show the notation. We should be checking the limit as x approaches 1, negative 1 from the left of f. Does that equal the limit as x approaches negative 1 from the right? Here, does the limit as x approaches negative 1 from the left of the slopes equal the limit as x approaches negative 1 from the right of the slopes? A minus 3 equals b plus 2. Negative 2a equals negative 2. A equals 1. B equals negative 4. A is 1. A minus 3 is negative 2. Minus 2 is negative 4. Okay. What is the slopes of this piecewise equation? Well, for x's less than 0, my slopes would be a plus 0 because the slopes of b are 0. And for x is bigger than or equal to 0, the slopes are negative 5 sine x. Okay. Let's make sure we're continuous. b equals 5. Plugging in 0 into both of these, we get b equals 5. Making sure the slopes are the same, a equals 0. B is 5, A is 0. Okay, cool. Then to the last 2 pages, which are notational derivatives. 1 page of here you're given a table, just extract the information from the table. The other page where, hey, you need to extract the information from the graph. And I'm not going to do the top part. Just like get there. Okay, notational derivatives. No, keep going around. It's the last door on your right. Here's the notational derivative. It's predicated upon you understanding that f's slopes are f's slopes. But you have to show it, the notation. G's slopes are G's slopes. What happens if you put a number in front of it? Okay, well, the number stays because like 4 sine x's slopes are 4 cosine x. What if you put a number underneath it? That number's going to stay underneath it. It's just like a third times G. But what if you multiply 2 functions together? Well, it's not as easy, just like it isn't easy with x's. You have to use your rules. Okay? So like the first 2 are going to be easy, but once we get here, you realize you got to use your rules. We'll talk about the different things to do with like a 2 here or a 2 there. All right. I'm going to go shorthand. I'm not going to say g prime of x and f prime of x, but you could. K prime of pi is equal to g prime of pi, or the slope of g at pi, which is -4. F prime of pi, slope of f at pi is -1. I get my answer -5. That's it. Done. What if I have constants? Well, again, constants don't bother us. We just leave them. You don't use the product rule. You don't say the slope of 3 is 0. You don't use the quotient rule. You don't say the slope of 4 is 0. They're just constants, just like you would not do anything crazy with this 3. Instead, the 3 stays, and you multiply the 3 and the 4, and you get a 12. So like the 3 doesn't go away, you don't do anything to it. Okay. Here we go. We got the slope of f at 2. The slope of f at 2 is -2. So I'll get -6. The slope of g at 2. The slope of g at 2 is -1. So this is -1/4. So -25/4. What about this 2 here? 2 different ways to do it. I like to say you can either bake it in or leave it out. What do I mean, bake it in? Well, first of all, you got to understand this is a product. Product, x's times x's. But what do you do with the 2? You can either bake it in or leave it out. What do I mean by that? I feel like I'm repeating myself. The slopes of 2g, 2g prime. That's the slopes of the first times the second. Plus the slopes of the second times the first. We say the first is 2g. This is what it means to bake it in. Just put it in as part of your product. What do I mean by leave it out? Leave it out says just worry about the 2 later and just do g times f. So say your derivative is, your slopes are 2 times slopes of the first times the second plus the slopes of the second times the first. You'll see you either have it distributed in or you'll distribute it in later. All right, slopes of g at 2 are -1. F at 2 is 4. Slopes of f at 2 are -2. G of 2 is 3. You get -8 minus 12, which is -20. If you add that, -6, -4 is -10. What about this x? It's still a product. Watch how this works. The slopes of h would be slopes of the first times the second plus the slopes of the second times the first. Slope of h at 3, g of 3 is 4, g prime of 3 is -2 times 3, because we're talking about x. This will be -2. Quotient rule. Slopes of g times f minus the slopes of f times g all over f's y value squared at 4. Slopes of g at 4 is -3. F at 4 is 3. I need my mouse. I'll be right back. Just be a lot faster with my mouse. All right. This will be easier. F of 4 is 3. F prime of 4 is -4. G of 4 is 2. F of 4 is 3 squared. Make sure G prime of 4 is -4. Okay. So -9 plus 8 over 9 is -1/9. Right. Okay. Let's do another one. What about this too? Like, oh, it's up to you. You could leave it out. If you wanted to, you'd have a 1/2 in front, slopes of the top times the bottom minus the slopes of the bottom times the top, all over the bottom squared. It's probably easier to do that and just multiply it in the end than it is to bake it into the bottom. There'd be a lot of 2's everywhere. So r prime of 2 would be 1/2 times 4 f of 2, which is 4. F prime of 2 is -2 times 2 squared over f of 2, which was 4 squared, which is 16. 16 plus 8 is 24 divided by 2 is 12. I get 12/16, which simplifies to be 6 3/4. I'm not going to spend my time getting the answers. You can go ahead and get the answer. I just want to make sure we have the correct slope equation. Product rule. I mean, it's actually easy. This one's easy to do. Cosine of pi is -1, the sine of pi is 0, so that's going to be a 0. So I have g prime of pi times -1. G prime of pi is -4 times -1, so this is going to be 4. What about this? Same deal. No worries. 6x g plus slopes of g times 3x squared. You are allowed to say g then g prime. You don't have to have of x if you want to do it for short or not. It's up to you. 18 g of 3. G of 3 is 4. G prime of 3, slopes of g at 3 are -2. Whatever that is. All right, now What if I give you a graph? I think the key is just to understand these are all straight lines. We know what the slopes are just by looking at the rise over the run, what the slopes are of G and F at all these points. Now, what don't we know is the slopes of the sharp points. The slopes of the sharp points do not exist. Next, we can look at the functions and find the y values, right? The question is like, what is f of -3? Well, -1, 2, 3. This is -3. F of -3 is this y value. We'll call it 1. What is f prime? It's the slope of f at -3. That is -1. So like y value, m value, y value, m value. You could go ahead and find that, but we're going to have to do that anyways for all these. Why did I do this? Okay, 3.25, sure. 1/2, not going to bother. F's slopes. F slopes at 3.25. 1, 2, 3.25. It doesn't matter. It's the slope of this line segment or the slope of this line segment. Slope of this line segment is 2. Slope of this line segment is -3. Cool. So the slope of F is -3. The slope of G is 2. -3/2 plus 4/2, 1/2. What about -2? Slope of that line segment is -1. The slope of this line segment is 0. So I have 2 F slopes minus 7 G slopes. Well, G slopes are 0, so that's nice. So I just have 2 times F slopes. I get -2 as my answer. But don't forget about your rules. Slopes of the first times the second plus the slopes of the second times the first. Notational derivatives. Now, being able to interpret it. Let's go back to understanding f prime of 1, g of 1. G prime of 1, f of 1. F's slope at 1, G's value at 1. G's slope is 1, f of 1. At 1, G's value is 1, 2, 3, 4. F's value is -1. F's slope, the slope of this line segment is 0. F slopes are 0. G slopes are 1. So we have -1. Slopes of the first times the second plus the slopes of the second times the first at -3. F of -3 is 1. F slope is -1. I'm plugging in -3 in for x. I get 4. Probably best to leave out the 3/2 and do G slopes times F minus F slopes times G all over F squared. You could bake it in, but it's going to be messy. All right, we're talking about 1. Okay. At 1, F slope is 0. So let's get rid of this part. F's value is -1 squared, which will be +1. G's slope is 1. F's value is -1. Oh, look at that. I answered that nicely. Quotient rule. Slopes of the top times the bottom minus the slopes of the bottom times the top over the bottom squared. G at 4. G of 4 is -1. G prime is -3 times 8. -1 squared. G of 4 is the red line. Negative. So -2 plus 24 is 22. F slopes at 1, 0. 2 times 1 times g of 1. G of 1 is 1, 2, 3, 4. G slope is 1. I don't like how I use that. 9. Distribute the x if you want, or I'm not gonna get the answer to this. Slopes of the first times the second plus the slopes of the second. Putting that minus 0 in because like minus 3 slopes are minus 0 times the first. Plugging in -1 everywhere, you get an answer. If you skip this one, I don't care. Okay. Lots of good work, lots of different types of problems, notational problems, second, third, fourth derivative problems, secant, cosecant, tangent, cotangent, all of those. So it's a good kind of like break from rules to do tricky problems. We have one more rule, one more lesson next class. Right? Peace.